So today we want to talk a little bit about Chapter 7, which is the Central Limit Theorem. And the idea here is that one of our biggest goals in statistics is to make an approximation of the parameter. So the parameter being the number associated to the population, it could be things like the average for the population. So for instance, suppose that we're talking about height, then it'd be the average height if you look at the entire population. And of course, to take a guess at that, we're going to use a sample. We'll take a sample of people and then figure out what their average height is, and then use that as an approximation for the actual parameter, the actual average height for all people. The issue here is that we want to know how close we're actually going to get. Similarly, we could look at the percentage of people that satisfy something. What's the percentage of people with brown hair, for example? And that there's an actual percentage for the entire population, the parameter, and our goal is to actually get as close as possible to that, or what percentage of people are going to vote for so-and-so in the upcoming election. And again, we want to try to get really close to that. And that's where the central limit theorem comes into play. So what the central limit theorem does is it basically tells us that when we look at samples of a certain size, if they're simple random samples, we're actually going to get pretty close to the actual parameter that we're looking for, because when we look at samples of a certain size, the statistics, the numbers that we get from them, the averages from the sample or the percentages, the proportions from those samples are going to fit a normal distribution. And we already know how to look at normal distributions with z-scores and z-score tables and things of that nature. So let's kind of get into what this is really talking about. The first one is that there's a distribution of sample means. And what this means is that if I look at samples of size n, so n is the sample size, if I was to look at a bunch of samples, so not just one sample, say I took like 100 samples and they're all of size n. So let's say that I asked 50 people every single time and they're all simple random samples. Then when I look at those samples, if I start to put down their means on a distribution, I'll get something that actually looks like a normal distribution. So like a bell curve. And the mean of the averages that I get from the sample. So what I mean here is the observations that I'm putting on my chart are actual sample means. So for instance, say I take 50 people and I find out that their mean, so I do it the first time, and their mean is 25. And I take another 50 people and their mean is 26. And I take another 50 people and their mean is 24. And I take another 50 people and their mean is 25. And so on and so forth. Each of these numbers is associated to a sample, and each of these numbers is a mean. So these are just sample means. Now, if I count up the number of samples that had 25 as their mean, it's going to end up being probably pretty large depending on whatever I'm actually measuring. And as I get further and further away from this, I get 24 and I get 26 and so on and so forth. What I'll end up seeing is that I get a distribution. And that distribution is going to have an average, since it is just a normal distribution. And the average, so this mu with a little x underneath it, that is the average for the distribution. So the average from the distribution is going to be equal to the average of the population. And that makes sense, because the more samples you take, the more likely it is that you're going to get closer and closer to, most of those samples are going to be close to the actual average, their averages will be. Every distribution has a standard deviation that describes how it tapers away. And the standard deviation for the distribution, which is that sigma with the x, so this is the standard deviation for the distribution, that is equal to the standard deviation for the population divided by the square root of n, where n is the sample space. Right, so that's the sample space, n is the sample space. Once we have all this information, we can actually figure out things that go along with the z-score table. So the biggest thing right now is wrapping your head around the idea that there is a distribution of sample means, which means that the observations are the averages for individual samples, all of the same size. So let me give you an example. So suppose that the mean is equal to 12. and the standard deviation of the population is equal to 2. So you can make this up whatever you want it to be. Maybe 12 is the head circumference of a small animal, and 2 is the standard deviation. That's how far off you could be. So that's the actual average for whatever small animal we're measuring. If you look at every single one of those small animals, 12 is the average, and the standard deviation would be 2. Now, suppose that I look at samples of size 100. And suppose that I want to know what's the probability that I get a sample that has larger than 12.5. So again, the probability that I get a sample of size 100 whose average is larger than 12.5. I can actually compute this because I've got a distribution. The mean of this distribution is equal to the mean of the population. The standard deviation, now this is kind of funny, the standard deviation of this particular distribution is equal to the standard deviation of the population, which we happen to know is 2, divided by the square root of 100, which is the number of people in our sample. Because we have so many people, it makes it difficult to get too far off. So I have 2 divided by 10, which is equal to 0.2. So the standard deviation for my distribution is 0.2. So this is 12.2, this is 12.4, this is 12.6, and this is 11.8, and 11.6, and 11.4. So my question is, what is the probability of getting a sample whose mean is larger than 12.5? I'm really looking for this area right here. And it's pretty small. Well, how do I figure that out? Well, my observation is 12.5, my mean is 12, my standard deviation is 0.2, so I just use a z-score table. So I compute my z-score, and that's equal to 12.5 minus 12 divided by 0.2, which is equal to 2.5. And then I look that up on the z-score table, and when I look it up on the z-score table, I get 0.9938, which corresponds to this side, but I want the other side, so I subtract it from 1. So I take 1 minus 0.9938, and I get 0.0062, which means that there is a 0.62% chance. Why is that remarkable? This is remarkable because what this says is, what if I didn't know the mean and I didn't know the standard deviation? Well, I do need to know the standard deviation, which we'll get to this in future chapters, how we kind of get around this issue. But what if I didn't know the mean? What this tells me is if I take a sample of size 100, I've got a 0.62% chance of getting something that's only 0.5 larger than the actual mean. In other words, I'm going to land pretty darn close to the actual mean. And so this is what the central limit theorem allows us to do. It allows us to realize that because this distribution exists, by finding statistics, we're using simple random samples, odds are we're going to get a number that's pretty close to what we want it to be. There's also a distribution of sample proportions. And so again, the same idea. You take a bunch of samples, you take their proportions. So a sample of 100, you check how many people have brown hair, maybe you get 38%. Sample of 100, you take how many people have brown hair, maybe you get 42%. Sample of 100, you take how many people have brown hair, maybe you get 41%. And you keep on doing this, and you keep on taking samples of 100. Now this distribution has a distribution mean, and that distribution mean is P. P corresponds to the proportion for the actual population. So if the actual population is 41% has brown hair, it would be 41%. So P, and it's in decimal. So this is the percent for the population in decimal form. And then that's the same thing here. It shows up down here and down here. So when you're doing the standard deviation of the distribution, you take that P and you plug it in as well. And again, is the number of people in our sample. So let's do an example for this one. So suppose that P is 42%. Let's suppose that the actual percentage of people that have, you could do brown hair if you wanted to, and let's say it's 42%. And then let's say that we're going to take a sample of size 1,000. We could ask, what's the probability that in our sample of 1,000, we get less than 40%, or 40% or less? And the way that we do this is, first of all, we'd figure out the mean for the distribution. The P with a little hat on it corresponds to, these are sample proportions. So the mean of this distribution is equal to 0.42, since that's the actual percentage. And the standard deviation for this distribution is equal to the square root of 0.42 times 1 minus 0.42 divided by 1,000. And so the standard deviation in this case, if you plug it all in, you get 0.0156. So now again, you've got a distribution mean, you've got a distribution standard deviation, so you can get a z-score. So now the z-score is equal to, well, we want our observation is 40%, so we're looking at 0.4. So we do 0.40 minus 0.42 divided by 0.0156, and we end up getting negative 1.28. You look this up on the table. We have a z-score table, and on the z-score table it corresponds to a percentage of 0.1003. We want 40% or less, so we keep this number, move the decimal place 2 spots, and we get 10.03%. So now, if the real percentage for the population is 42%, and we look at sample sizes of 1,000, the odds that we get something 40% or less, which is only 2% off, is 10%. It's not very likely that you actually get that. In fact, this is where you start to realize that when you hear of people saying, we did a sample size 1,000, we believe this percentage of people are going to vote for so-and-so, give or take 3%, it comes from the central limit theorem, and that's what we're going to see next time.